How many have heard of Ohm's law in physics? Okay, voltage equals current times resistance. Yes. Thank you, Eric. Thank you, Chris. All right, let me give you a moment to copy this example down. Okay, all right. So let's see here. The voltage in a simple electrical circuit is slowly decreasing as the battery wears out. Okay, the resistance R is slowly increasing as the resistor heats up. Okay, so, all right. We want to use Ohm's law, which says that voltage is equal to current times resistance, to find how the current is changing at the moment when the resistance is equal to 400. What's that? What's this symbol stand for? This symbol here. Good, Chris. 400 ohms. Current equals 0.08. What's A? Amperes. Good, Chris. Good, Ryan. Okay, and then you have these rates at which for volts per second. Okay, and does it make sense that that dV dt is negative, that the rate's negative? Absolutely, that's right, Ryan. Because it says that the voltage is slowly decreasing as the battery wears out. And then, of course, since the resistance is so slowly increasing with time, dR dt would be positive 0.03. Okay. Now, what we're going to do here is I'm going to try to solve this problem right on the whiteboard. Okay? I'm going to try to solve it right on the whiteboard, and bear with me here. Is everybody good so far? All right. Wonderful. Name is good. Thank you. All right. Let me go ahead then and get to the whiteboard. Okay. All right. So, got my little pen here. Got my little pen. Okay. So, in the problem. Okay, and let me just hold on. Click these pages together. So they want us to find how the current is changing at the moment when, they specify those values. So what are we looking to find here? What are we looking to find? D something. D something. Find how the current is changing at the moment. Good. That's right, Ryan. We want to find di dt. Okay. But the thing is, we have to remember is that because voltage equals I times R, that means I is going to equal voltage divided by R, by resistance, or V times R to the negative first power. All right. And incidentally, V, well, let's do a little, maybe a little schematic here. So so I have my current. If I do a little flow chart, current is a function of voltage and resistance, right? But with that, am I going to be able to find di dt based on my flow chart here? Am I going to be able to find that derivative, or do I need to extend my flow chart? Could I extend the flow chart? Current is a function of voltage and resistance. Voltage is a function of what? Does voltage stay constant here? No, voltage is decreasing. So voltage is a function of what variable? That's right. Good. Voltage is a function of time, and resistance is a function of time also. So if I'm going to find di dt, I have to take into account both links of the chain. There are two links in this chain. Okay. So, all right, let's think about this for a moment. So, what's going to determine how current varies with time? Well, first of all, how the voltage varies with, oh, sorry, I got that wrong. Hold on. Trying to get this. Based on the flow chart, current varies. Current is a function of voltage, right? Current is a function of voltage, but voltage is a function of time. So if we look at the rate, if we think about the rate as current varies with the voltage times the rate at which voltage varies with time, well, okay, and these are partial derivatives. These are partial derivatives here, but here these are just regular derivatives because voltage is a function of one variable. But are the units going to be correct? The units are what is it? Amperes. The units for the rate are amperes per unit time. Is that going to work here? Well, in this, if we think about those derivatives simplifying out, we have di over dt. But is there anything else that we need to consider when we want to compute the rate, this rate, di dt? We took voltage into account. What else do we need to take into account? The resistance. Good, Ryan. All right. So then I'm going to have then here the partial derivative of I with respect to V. No, with respect to R times what's going to go here? These aren't dot products. I'm just drawing the times a little. They're not dot products. They're multiplies. But good, Ryan. dr dt. Very good. And again, the partials, the rate, the differentials cancel, and you're left with di dt. So what I'm trying to say is, I always think in terms of units. The units for my derivative are amperes per unit time. Actually, T isn't right. It would be amperes per what? Per amperes per second, right? So the units are amperes per second, and I got those units. So you see, this is the chain rule. We're doing a chain rule. in multivariable calculus. Are there any questions so far? Who's feeling comfortable? Is there anybody uncomfortable? We'll do some more examples, but all right, well, what's the partial derivative of I with respect to V? Based on this formula here, what's the partial derivative of I with respect to V? So let me just put so I need something to go in here. It's a partial derivative. I is equal to V times R to the negative first. So what would the partial derivative of I with respect to V be? That's right. Good, Robin. 1 over R to the negative first. Okay, now we got to do this part. What's the partial derivative of I with respect to R based on this formula? Good. That's right, Christopher. Negative V over R squared. Okay. And so we're going to get 1 over R times dV dt minus V over R squared times dr dt. Now we just plug in our numbers. So resistance was 400 ohms. Okay. Let me see here. What was dV dt? What was dV dt equal to? In the problem? Well, you copied it down. dV dt is equal to negative, good, Ryan, negative 0.01. Okay, let me make that a little bit nicer here. Hold on. So it goes a little slower this way, but it's okay. Hold on. Okay, let me try this again. Yeah, so this is negative 0.01. And then V was, let's see, Well, how are we going to find V? How are we going to find V? Right, good, Ryan. V equals I times R. So that means that V, V. Well, yeah, that's right. V equals I times R. So hold on here. Let me just see here. One moment. Oh, okay. So in the denominator, R squared would be 400 squared. And in the numerator, the V would just be 0.08 times 400. Because V is equal to I times R. And then dr dt is just 0.03. Are there any questions up to that step? All right. Well, if you work it out, then you're going to get negative 0.000031, and the units are going to be amperes per second. That's the answer. That's your rate. And we use the chain rule. Now the book has formulas for different, well, I just want to do a few more examples, and I can then show you a few formulas in the book. But if we use our intuition here, we can make this very simple. I'm not about memorizing a bunch of formulas, because it's not it's not necessary, because we can just draw our flow chart here, for each problem. But of course, it is nice to see the formulas just to give context. But we'll do that in a little bit. All right. Are there any questions? Any questions on this? Okay. May I go to another example? Maybe give me a thumbs up if you're ready. Okay, John's ready. Good. Ryan's ready. Everybody's ready. Okay, let's go to another example. Thank you, everyone. Okay, let me give you a moment to copy down this example. All right. Okay, so here, um, let's take a look at what we got here. We have a function, u is a function of, well, u is a function, in this case, of how many variables? How many variables, in this case, is u a function of? Three. That's right. That's right, Robin. Three. And, okay, and x and y and z are themselves functions of variables r, s, and t. So we want to find the value. We want to see how does u vary with respect to s when r equals 2, s equals 1, and t equals 0. Okay, so let's take a look at this. How would we start the problem? What would help us a lot in starting the problem? Well, what helped us in the last problem to feel comfortable? A sketch. Good, Deodat, a sketch. Okay. Well, all right. Let's go and do a sketch. So, all right, let's go to that whiteboard again. Okay, I'm really using it a lot today. I usually, but you know, it's good to try things. All right, so let's see. Let's see. All right, so, all right, u is a function of x, y, and z, and x, y, and z are, well, x is a function of r, s, and t. Y is a function of r, s, and t. And z is a function of r, s, and t. Okay. It's like cooking, I don't know, it's like taking a, I think of it, you ever sit on a chair where the legs are kind of wobbly? You know, have you ever sat on a chair where the legs are kind of wobbly? That's what this kind of reminds me of. U is a function of x, y, and z. So think of a chair with three legs, x, y, and z. As x, y, and z change, u changes. So u vary. How u varies depends on x, y, and z. But in turn, x, y, and z each vary with r, s, and t. All right. So now what we have to do is we have to, based on this, create a chain rule. Okay, so how many links are there in this chain? Three. Good, Robin. Good. So, okay. Well, all right. I start off with partial of u with respect to s. Okay. So what's going to be, there are three links. Hold on here. Three links. So a partial, well, I'm setting it up for you. And this is a times, these are times. Let's Try to get this good. Okay, so I have to put in rates everywhere, derivatives everywhere. And I'm going to use the flow chart to help me create my chain rule, So what if I put a partial of u here? What's going to go in the denominator? Partial of what variable? Good. Good, Robin. Let me know if you have any questions. Okay. But remember, the rate is how you change this with respect to s. So all of my 1, 2, 3 pieces of the chain have to be that rate. So okay, I'm going to multiply the partial derivative of u with respect to x. So now, I'm moving down. Hold on here. Yeah. I'm moving down the first link here. Partial of u with respect to x times d something times d something. Well, all right, but what's going to go up here? D something. What would it have to be? Good. That's right, Eric. Very good. Dx ds. Okay. And again, you can kind of check yourself by saying, okay, I can, I'm not like, that isn't like I'm actually simplifying those out. I'm just sort of showing it pictorially that, hey, the rate is correct. The rate is correct for, for that length. Okay, now what's going to go then in the next part? Now I need to go down the second link. So what's going to go here in this second part? What partial derivative? Good. Partial of u with respect to y. Very good. Very good. Partial of u with respect to y times then d something. D. Good, Eric. dy ds. Now, why do I have a dy ds here? Why don't I have the partial derivative of y? Oh, wait, hold on. Actually, I do have a little error here. I actually do have an error. These derivatives are partial derivatives, right? So x was a function of 3 variables. So I have to have the partial derivative of x with respect to s, because I'm going to hold t and r constant there. And then here I have to have the partial derivative of y with respect to x, because y is a function of more than one variable. Okay. And then finally, the last link is going to be the partial of u with respect to z times the partial of z with respect to s. You see how this is working? Are there any questions? All right, Jamal's comfortable and Robin's comfortable. All right. Well, now that we got the rule set up, it's just a matter of computing partial derivatives. So the partial derivative of u with respect to x is going to be 4x cubed times y. The partial derivative of x with respect to s is going to be r times e to the t. Okay. All right. And maybe I'll work it this way. Okay, work horizontally. Now the next part is going to be something times something. And then the next part is going to be, so we have here 4x cubed y times r to the et power. And then we have two more links we have to fill in. So I want you to take a moment and see if you can fill in the missing holes there. Okay, take it, and then I'll write them in. I mean, I could just write them in, but let's see if you can do it and see if you're right. Okay, let me go ahead and fill in what's here. So here you should have, hold on here, I just got to get oriented. Okay, so here you should have x to the fourth plus 2y z cubed. And then here you should have 2r s e. I didn't make these big enough, did I? Two rs e to the negative z power. And you know who's getting these? Who's getting this? Okay, John got that. Wonderful. And Ryan, good. And then here we're going to have 3x squared z squared times r squared times the sine of t. All right, who got those for that part? Okay, wonderful, John. Good, good, good. Let me know if you have any questions. Okay, so now what we have to do is we have to evaluate. And I was going to mention, you know, one time I actually, you know how like you use a function of x, y, and z, and x, y, and z are functions of r, s, and t, and we're trying to find the partial of u with respect to s. I actually saw one time a student actually take the, you know, x, y, and z are defined, right? those are defined. Those functions, in the example you copied, we defined the functions of x, y, and z. And the student actually plugged those in. Plug those in, like for these like 3 terms here, and then had a huge derivative, to work with. The huge function. We don't want to do that. We don't want to do that. I mean, let's see. Well, let's see. So let me continue over here. It would not be incorrect, Eric. It would not be incorrect. Well, yes, it would, Eric. It would be incorrect. No, it would not be incorrect, but it's not the way, I mean, like, I would not want to see that on an exam, right? Because it's because we want to utilize what we just did, the chain. Well, we want to utilize the chain rule. Look well, we did though utilize the chain rule, but here's what I'm trying to say. Here's what I'm trying to say. We know that R equals 2, S equals 1. Hold on, something happened here with my pen. I touched a button and it went kind of haywire. So I'm still learning. Oh gosh, don't hit that eraser. Okay, S equals 1 and T equals 0. Then if that's the case, then well, X is just going to equal 2 times 1 times e to the 0, which is 2, right? Because X is R times S times e to the t. So that would be 2 times 1 times e to the 0 power. Y would be equal to, what would it be? It would be 2 times 1 squared times e to the minus 0, which is 2. And then finally, z would equal 2 squared times 1 times the sine of 0, and that just gives us 0. And so, now wait, I want you to stay down there, not to flip up. Hold on here. So, the partial of u with respect to s, that rate, that partial derivative, when r equals 2, s equals 1, and t equals 0, is going to equal then, it's going to equal well, hold on, let me get this over. It's going to equal 64 times, I don't know why it does, we're okay, I'm just trying, 64 times 2. Oh, where's the 64 come from? Well, we have 4x cubed y, right, in the first link. So 64 is 4x cubed y. So that would be 4 times 2 cubed, because x is 2. No, wait. Yeah, 4 x cubed y would be 4 times 2 cubed times another 2. And so I get the 64 by going 4 times 2 cubed times 2. Okay. And then the r times e to the t, r times e to the t, the 2 here, just comes from r, 2 times e to the 0. That's how I'm getting that 2 there. Okay. Is this okay, or are you following all right? Are there any questions at all? Try to make this a little nicer over here. Okay, Ryan's good. Thank you, Ryan. All right, now the two other parts, you can work it out. You'll get 16 times 4 if you work it out. And 16 times 4 plus 0 times 0. Okay, why don't you see if you can confirm that, if you would. I'd like at least one confirmation. Hopefully I'm showing you enough here in this little video to help you, understand what's going on. Okay, Eric says it looks correct to him. All right, thank you, Eric. So you're going to get 192. Okay. That's the answer. That's your rate. And that is the part, that is how u varies with respect to x. That is the rate exactly when r equals 2, s equals 1, and t equals 0, the partial derivative of u with respect to x, we're evaluating that partial derivative when r equals 2, s equals 1, and t equals 0. That's going to equal 192. Okay. All right. Are there any questions on that? Any questions so far? All right. Let me bring up the ebook just for a moment here. Chain rule. All right, let me go into the ebook. All right, one moment here. All right, so I will go into the ebook. Okay, so the ebook talks about the chain rule, and it starts off with the chain rule that you learned in Calculus 1. Okay, this is can make this a little bigger here if I learned if I, good, if I double click, that'll make it bigger. And I think it'll do it for you too. I think it'll do it for you too. If you double click on your screen, I think it'll make it bigger. But you know, this here is the chain rule that you learned in Calculus 1. All right. And now what we're doing is we have other rules. We have new rules that we're coming up with. Okay, they have these different cases. Like this is a case where if z is a function of x and y, and x and y are functions of t only. Well, that's what the chain rule would look like. But I find it very helpful to draw that flow chart, because from the flow chart I can get the formula, I can get the chain rule. How many like drawing the flow chart first? Okay, Ryan likes that flow chart. Good, good. And Robin does. And all right, good, good. Well, all right. So if we, you know, continue in the book, they do some examples, and we did some examples. And then, you know, they have other cases. They have other cases. Like here's if z is a function of x and y, and x and y are functions of s and t, then your chain rule would look like that, and you could compute the partial derivatives of z with respect to s and t. Okay, they have all these rules, you know, all these chain rules. They have a general version, and you know, again, you know, that's fine. That's fine. So I want to look at another example. Okay, I want to look at another example here. Okay, another example. Okay, take a moment to copy this example down, and we'll talk about it. Okay, let's take a look here now at this. So, wow, you know, I have here x cubed plus y cubed equals 6xy. And I want to find y prime. In other words, I want to find dy dx. So to find dy dx, what am I going to have to do here? What procedure would you normally do to find dy dx, given that x cubed plus y cubed equals 6 times x times y? Think back to Calculus 1. Hold on. Well, you know, Ryan, you have an idea, set y, solve the equation for y, but I don't think we can solve the equation for y. I don't think we can, I mean, we know that y is implicitly a function of x, because if we put an x value in the equation, and we'll get a y value, and if we change the x value, we'll get a different y value. But Eric's right. We have to use implicit differentiation. Well, yes, in Calculus 1, you had to use implicit differentiation. But now that we know the chain rule, now that we know this chain rule, we don't need to use implicit differentiation. We can find a formula to help us. So let me show you how this works. Let me show you how this works. All right, I'll go to the whiteboard here. It's really quite fascinating. All right, so let me write down the let me write down the man, hold on. Uh-oh, the pen's going crazy. I don't know why. I think if I touch a certain button on this pen, it kind of goes crazy. I don't know why, but I just have to be careful, I guess. See, the thing is, these things they don't come with instructions anymore, you know? I guess you have to look on the internet to find the instructions, right? All right. Used to be when you bought something, class, you open the box and there will be an instruction manual. You didn't have to, there wasn't an internet to go on to find the instruction manual. But now you got to kind of look for it on the internet when you buy some. All right, so here we go. Now, on the left-hand side, I think you agree that this is, we can call this a big function of x and y. Okay, I mean, what I did was the 6xy I brought over to the other side. So my equation, I brought the 6xy over to the left side and wrote the equation like this. And so you see now my big function f is a function of x and y, certainly. We can see that based on the left-hand side of the equation. Okay, and y is a function of x. Okay, y is a function of x. We understand this implicitly, right? So the whole idea behind implicit differentiation is that we recognize that even though we can't solve y as a function of x, gosh, hold on, let me switch my chair here. One moment, class. Hang on. Okay, so y is a function of x implicitly. Okay, and of course x is a function of itself. Okay, so this is sort of the key to coming up with a formula to find the dy dx. Are we okay? Are you okay with this flow chart? All right. So, all right. Well, so what I'm going to do is I'm going to take the partial derivative with respect to x of, hold on, I want to do one more thing here. before I do that. I want to do one more thing. So I have this function of x and y, but given my flow chart, I could, well, no, it's okay. Let's leave it as is. Let's leave it as is. Okay, so I'm gonna differentiate both sides of this equation with respect to x. And I'm going to take the partial derivative of the function on the left, the function of x and y. But I have to write, of course, that y is a function of x, because y is a function of x implicitly. Here I have f is a function of x and y, but I could write it. I could write the y as a function of x here. And really, I should do that because y is implicitly a function of x. Okay? I really need to do that. Okay, so I'm taking partial derivatives of both sides with respect to x. And now, on the left-hand side, based on the flow chart, how many links are there to the chain? Well, there are going to be 2 links. There are going to be 2 links. So the first is going to be what partial derivative? Partial of blank with respect to blank. I think we know the bottom is x. What's going to be in the top? Good. And incidentally, we can put over here, while we're at it, we can put the partial of f with respect to what? With respect to y. Good, good. All right, because you know, this is like the first level of my, my flow chart. But now I got to get the next level of the flow chart. And the next level of the flow chart is this level here. So for that level, I'm going to have, all right, well, so what's going to go here? What's going to go in this spot? Good, Eric. Good. It's going to be dx dx. Absolutely. And over here, that equals 1, absolutely. And then what's going to go in this spot? dy dx, good. Okay, this is working okay. And so now, can I solve this equation for dy dx? Yeah, that's right. A nice, clean, solvable formula. That's right. That's right. So now dy dx is just going to equal, well, I'll tell you what, let me not, I don't want to skip too many steps here. So we have the partial derivative of f with respect to y equals negative partial of f with respect to x. And so dy dx will equal, good, negative partial of f with respect to x divided by partial of f with respect to y. Or you can think of it, you can write it this way, negative of there you go. Now you have a formula, so you can do implicit differentiation for, now this will be calculus 1 implicit differentiation. You're finding dy dx, so be a little careful. I know, you know, this won't work for the the section 11.3 implicit differentiation that you did, because you're finding dy dx. You're not finding the partial derivative of y with respect to x. But nevertheless, for, you know, calculus 1, I mean, this, I mean, how many think, man, I should have learned calculus 3 before calculus 1, and then I'd have a nice formula to do implicit differentiation. I mean, how many think this is pretty cool? Yeah, Deodat knows what I'm talking about, and John and Robin. All right, great. Great. Well, all right. So let's go ahead. Yeah, Eric, it would have helped then. Well, yeah, and Eric, the other Eric, it would have been interesting if you, yeah, you had to take Calc 1 before Calculus 3. All right, so dy dx is equal to the negative of the ratio of these partial derivatives. And so that's the partial derivative of f with big F with respect to x is just 3x squared minus 6y. And the partial derivative of f with respect to y is just 3y squared minus 6x. Okay, that's the answer. And you could simplify this and get negative x squared minus 2y, all divided by y squared minus 2x. Okay. So there you go. I mean, it's pretty cool that you can use the chain rule to help you with implicit differentiation. Now, I want to mention also in the book, in section 11.5, for the chain rule section, they do have some formulas to compute partial derivatives where when you have an equation and you have to define a big function f, but for the exam, you cannot like utilize this chain rule. Okay, you cannot. You have to do like implicit differentiation the way section 11.3 taught you implicit differentiation. Okay, so all right. Are there any questions on that?
Wait, so we can't do what we did right here, or what do you mean?
On the exam, for a problem like a section that comes from section 11.3, you have to use the technique in section 11.3 to solve that problem. So, like as you recall, Ryan, in section 11.3, yeah, you had some. I mean, this here is implicit differentiation, and we got a formula to find dy dx. But in section 11.3, what you were doing was you were using implicit differentiation to define hold on, let me just look back here. Yeah, you did implicit partial differentiation. This is not implicit. This formula here is not for implicit partial differentiation. That's what I'm trying to say. Okay, and so, all right. Okay, that's really the key idea behind section. These are the key ideas behind the section 11.5. I'm going to show you one more thing. You know, what about, like, could we use a chain rule to compute a second partial derivative? Could we compute a chain rule to compute a second partial derivative? Okay, I mean that's you can. That's right. Absolutely, absolutely. And if we go to the ebook here, hold on, class. Let me get into the ebook. Okay. If we get in there, if we go, see, they have all these flow charts. But example 7 here talks about finding if you have a function of x and y, okay, and hold on, yeah, let me make that a little bit bigger. If you have a function of just trying to make it a little bigger. I don't know if it, I mean, it was working. Click, click. There we go. Guess it takes time. Yeah, here in example 7, you have a function of x and y, and x and y are themselves functions of R and S. And so, you know, no problem finding the first partial derivative. That's easy enough to do. But the second partial derivative is quite, it's somewhat complicated. Okay, and to me, like they have flow charts here and they show how to work it out. I think in your homework there may be a problem that deals with this, but there will be a watch it video to help you. And we're not going to be doing a lot of second partial derivatives in with the chain rule, but you should be aware of how they work. So, you know, the chains they can get quite interesting to compute. All right, are there any questions? I will stop the recording if there are no questions. Okay.